Okay, so we're going to do a famous birthday problem. Maybe some of you have heard it in class before or somewhere else. So I'm going to start saying, in a group of 10 people, what is the probability that at least 2 of them have the same birthday? And this is one of those problems where, first of all, it's going to be striking the results. Maybe not for 10, but in my second example, I'm going to change it. But the second thing I want to say is that it's one of those things that the clue idea is to not find the probability of this event because it's hard, but to find the probability of the complement of this event and subtract from 1. So if it didn't happen that in a group of 10, at least 2 of them had the same birthday, if that did not happen, what did happen is that all 10 have different birthdays, right? So I'm going to find, instead of finding this, solve this question, I'm going to answer, find a probability of all different birthdays. Okay, if I find that, the question I was asked is going to be 1 minus that, right? It's a complement. So between the two probabilities, it has to be 1. So if just the key idea is that if it didn't happen, then at least 2 of them had the same birthday, right? If you have a group of people and you ask them when was their birthday and none of them matched, so what did happen is that all 10 were different. So how am I going to count this probability? Well, let's do it like this. I have I'm going to divide by how many possible ways can 10 people have 10 different birthdays. And by numerator is going to be how many ways can I get 10 people to have 10 different birthdays. If you think about it, I like to think about it all in terms of passwords or license plates or stuff like that. I have 10 spots, 3, 4, 5, 6, 7, 8, 9, 10, to be filled with days of the year. Right. Of course, there's a big assumption here. We're assuming that every day of the year, every person is equally likely to be born on any day of the year. And that might not be true for different reasons, but let's assume that that's true because that's a big assumption here. So if every day of the year, it's equally likely for anybody to be to have his birthday, then what I'm trying to count is how many ways can I fill 10 spots with 10 different days of the calendar. That's all I'm saying. Like if you had 365, if you have a symbol for each day of the calendar, then I need to fill these 10 spots with 10 different symbols, right? I'm saying symbols because they're not alphabet. We don't have enough for 365 different letters. So, and of course we're excluding leap years and all that. Every year is 365 for these purposes. So, so we know how to do that, right? The first person could have, the first spot could be filled by any of 365 days of the year, but I'm counting all different days. So the next one is going to be 364, right? If I don't want to repeat birthdays, the next one is 363, and so on, right? So this turns out to be 356, I believe. Sorry, the last one. Right, that will make it to be 10. But I'm going to multiply those, right? But this is that's why we didn't do this problem before. It's not that we can't do this. It's just like, well, we have a better way to write this now. This is exactly 365 P10, right? So I'm selecting 10 from a group of 365. And they cannot be repeated. The objects in this case are the days of the year, and I'm selecting 10 of them, right? So that's how many ways I can select 10 days of the year that are different, right, randomly. So that's my numerator. So this is going to be the probability. Oops, sorry. Went too far. There you go. So if I do 365 P10 divided by, now the denominator is going to be of all, how many ways can I get 365 days regardless if they're repeating or not, right? So for my denominators, how many ways are there to have 365 fill these 10 spots, if you want to think it that way, with no restrictions, where it could be anything, right? So now the first letter could have been, or the first symbol, the first day of in this collection of 10 could have been any of the 365 days. My second one could have been any other 365 days, and so on. So my denominator is 365 to the power of 10, right? 65 times 65 times 65 to the power of 10. So that's the probability of the 10 people having all different birthdays. Yeah, in the numerator, I'm filling that with 10 different birthdays, 10 different days, and the denominator, I'm filling it with no restrictions, so it could be any. They could repeat. So these are big numbers. So of course we have a calculator for that here, and I can write NPR 365, 10. So that's a huge number, right? How many possible ways can I get 10 different days of the year? And I don't need to do it in 2 steps, but if you want to see how big is 365 to the power of 10, of course that's huge, right? But look at that. They're both of the same magnitude, right? So when I divide them, they both are 10 to the 25. It's not going to be unmanageable for the calculator, for the computer. So in this calculator, I'm going to show you that I can even just like this, right? Here I can just divide here, press the division button, and say divided by 365 to the power of 10. So it's 88% chance that there were nobody repeated birthday in a group of 10. So my answer is going to be 1 minus that, right? I can just do it right here if I type 1 minus. Oh no, I couldn't do it. Can I go outside there? 1 minus. There you go. So 1 minus that is 0.11, so close to 12%. So 1169. So this is going to be 0.1169. Okay, so there's about 12% chance that 2 people have the same birthday. So this was the 88%. So 1 minus 88% is about 12%. Okay, let me change that. I'm going to do the same thing with 30 people. And in the classroom, when I have 30 people in its full class, I ask who was born in January, who was born in February, March, go along the year. And I have done it many times, probably 12, 15 times. And only once there was no repeated birthday in the classroom. Okay? And this is one of those probably the examples that it strikes people's head. Because if I do 30, you'll see what's going to happen. I don't have to go over the processes again. If you see what we did, it's going to be, again, it's going to be, if you follow the idea, it's going to be, it's going to be 1 minus the probability of no repeated birthdays. And following the same logic as before, no repeated birthday is going to be 365 P30 in the numerator. The denominator is going to be 365 to the power of 30, right? In the numerator, I'm picking 30 different objects from a group of 365. The objects are the days of the year. I'm picking 365 different days. In the denominator, I'm creating all possible chains of length 30 with no restrictions from the group of 365 days of the year. So let's find that directly up here. I can just change here this number for a 30 and that denominator for a 30 right there. So it's 70%. So in a group of 30, there is 70%, 70.6% chance that 2 have the same birthday. So this is very striking for the first time you see this. I hope you get surprised by this. It is, and it's around, I think it's around 23 where this changes to be more likely than not that this is around 50%. So if let me erase this so we don't get confused. So if I put here on 23, right, doubts could be, if I do it with 23 people, it would be that, right? So for 23 people, the probability is already more than 50%. I already have here the 1 minus, right? So this is already what the probability of having two different birthdays. Sorry, of at least two people having the same birthday. If you have a group of 40, this gets, let me just do it with 43 because that's easy to change here. 92%. So, yeah, so it's a good exercise if you're in a party with 40 people and you don't know most of them, you want to have an excuse to talk to everybody in the party. You can go around, ask them their different birthdays, and there's a big chance that you'll find two with the same birthday because there's 92% chance that it will happen.